Okay. How's everybody doing? How's the homework coming along? Okay, I have some smiles and head nods. I'm not sure if it's a smile or a grimace, but we'll hope for the best there. And so that's due on Friday, and then I'll get homework 2 posted soon, which will cover some of the stuff we've covered. Okay. All right. So again, big picture idea. Monte Carlo methods. Instead of doing the math and the integration, we just generate random values from some kind of target distribution. So far, all of the distributions that we've kind of played around with, maybe with the exception of the sine function, the top half of the sine function, most of them have been standard, well-studied distributions that exist, right? So we've been looking at, I don't know, the exponential distribution, the normal distribution, and I guess today we'll kind of continue that, but we're going to look at, what if we wanted to generate like multiple random variables from a joint distribution. Okay, so far all of our examples have been univariate, and today we'll look at kind of our first multivariate distribution, and we'll just start off with a standard one that is pretty well understood, and we'll do a little bit of a mathematical approach for it. Okay, in the future, as we go along, we're going to explore more complex multivariate distributions and strategies for getting samples from those. Okay, all right. So sorry, let me I have to fix my pen. Oops. Okay. So far, we've discussed random number generation, for variety of univariate probability distributions. Oh, before I continue, so I guess Stats Club is tonight. I sent an email. Nobody said anything, but this Saturday there's a hike with Professor Tsang, and you guys can join that. And then in a couple Saturdays I'll be going on a hike, and you guys are welcome to join me. It's I don't know, if you enjoy hiking, it's fun. I mean, if you don't like hiking, don't come. Because I'm there doesn't suddenly make it even more fun. It's just it's still hiking, and you have to be outside. And but anyway, in 2 Saturdays, on the 27th, we'll be hiking up to the Hollywood sign. If you've never been, it's kind of fun. You can't actually like touch the Hollywood sign; it's all fenced off, but you can see it kind of close. And then, but anyway, just but you got to sign up. Okay. All right. So we've discussed random number generation for a variety of univariate probability distributions, and so far we've looked at inverse CDF, rejection sampling, and then we had Box-Mueller for the normal. So this is like a transformation, and then we've had just briefly, convolutions and kind of using known relationships. Okay, so a lot of distributions are based on known relationships between things, and we've talked about this. Okay, so today we will take a look at our first multivariate distribution, and we will just start off with a kind of a well-known one, and this will be the bivariate normal distribution. Okay, and this is not the same thing as generating two independent normal values. Okay, so the bivariate normal distribution allows for covariance between the terms. Okay, between the variables. Okay, it is not the same as generating two independent normal values. Okay, because whenever you have a multivariate distribution, there could be covariance between the terms, right? If everything were independent, then we wouldn't have to worry about anything. But we know that relationships exist between variables, and so if we wanted to draw random values to kind of study these distributions, we need to also be able to include that covariance in the random values we generate. Okay, so the bivariate normal distribution may be, if we have x1 and x2, the bivariate normal distribution maybe would look something like this, where you can draw kind of contour lines for the density. Okay, now with the bivariate normal, if you kind of project down onto one distribution, one side only, okay, if you look at each variable on its own, sure, it would look like a normal distribution over there. Oh, I'm gonna lose this a little bit, but on the respective projections, it looks normal, but together they're clearly not independent, right? So and so if we define our vector x as x1 and x2, then we would say x comes from normal distribution of dimension 2 with a mean vector mu and variance covariance matrix sigma, okay, where mu is going to be the vector mu1, mu2, and the matrix sigma will be, sigma 1 squared, covariance of sigma 1, 2, sigma 1, 2, and sigma 2 squared. And, sigma 1, 2 is the covariance. And this is known as the expected value of the term x1 minus mu1, x2 minus mu2. Kind of the product of those things, right? What would our bivariate distribution look like if there's no covariance between x1 and x2, if they were independent? So just kind of an aside here. So x1 and x2 have no covariance. That is to say, x1 and x2 are independent, or we might say x1 independent x2, like that. Then your bivariate distribution, maybe it would look like this. Okay. And if we draw kind of the contour lines, you could draw, like if you had, this is supposed to be vertical. Basically, the axes of the ellipse have two L's, will be parallel to the x1 and x2 axes. Okay, and this is still a normal distribution. Over here we have less variance, but so here, the covariance is 0. But we want to know, can we come up with a general form that allows for there to be, positive or negative covariance between our x1 and x2 terms, not just the independent case. Okay. Well, to get there, we will. All right, so to produce random draws, from N2 from our bivariate normal, okay, we will begin by producing just random independent normal draws. So we'll produce the vector z coming from N2 with the 0 vector, and the covariance matrix being the identity matrix, right? So the 0 vector is that, and then so basically our mu vector is 0, and our covariance matrix is the identity. So it's, basically standard normal, right? So basically, if z is defined as z1 and z2, this is basically z1 comes from standard normal, and z2 also comes from standard normal, and z1 is independent of z2. Okay. So in this case, our bivariate normal plot would just be circles, concentric circles. Not just perpendicular, but they both have the same amount of variance. So we would get concentric circles here. Okay. And what we want is we will let x be defined as B plus matrix A times Z. Okay? And our goal is to find a matrix B, a vector B and a matrix A, so that after we apply this kind of transformation, we'll get the relationship that we want. We'll get the distribution that we want. Okay? So so we want to, so we'll find this so that x comes from the desired distribution. That x, we'll say so that x comes from the desired distribution. Okay. All right. So let's see if we can find the expected value of x, and see what needs to be done so that we can set the expected value of x equal to mu. Okay, so first we'll find the expected value of x and set it equal to the mu vector, right? And that way the expected value of our x variable will be what we want. All right, so x is defined as b plus a times z. All right, so we're going to do the expected value of x will be the expected value and this will break out to this plus that, okay? And furthermore, we can, A is a matrix that we're multiplying. So we'll multiply that by that, okay? And the expected value of z is going to be 0, right? So So this the expected value of z as we see up here is kind of our 0 vector. So we just get that, and thus the expected value of x is equal to the expected value of b, which is just our b vector. Okay, and so we will set b vector equal to the desired mu vector. Okay, so if we let x be defined as b plus az, okay, and we set the b vector equal to the mu vector, then the expected value of b will equal, I'm sorry, not the expected value of b, the expected value of x will equal mu. All right, great. All right, and then okay, same thing. So using the same idea here, we will find the variance covariance matrix of x and set it equal to sigma. Okay. So the variance covariance matrix of x will be the covariance of our x variable, and this will be the covariance of b plus a z. Okay. When you just add a constant term, that doesn't affect the covariance. So this just becomes this. All right. And then, and it's a little, I don't know if you guys know this rule, but basically if you have the, a constant multiplied by a term, univariate, and you pull it out of the variance, what happens to that constant? You square it, right? Okay. When we are dealing with matrix vector form, we're effectively squaring it, but because of the way the dimensions line up, you have to put one in the front and one in the transpose of it on the back. Okay, so this will become a covariance of z, a transpose. Okay, the covariance of z is the identity matrix, so we just get a transpose. Okay, all right, we set a transpose equal to the desired covariance matrix. Okay, and so now we need to find A, so that A transpose will equal our matrix sigma. All right. Okay, and lucky for us, we have some rules that can help us out, right? So, so there's a decomposition, matrix decomposition. I think this one is called spectral decomposition, although I hesitate to write it because it could be wrong. All right, but basically, for any symmetric, I don't know, you guys remember these things from your linear algebra class. Symmetric positive definite matrix sigma. Okay, which is the case because sigma is a covariance matrix. So all the variance covariance matrices are symmetric positive definite. Okay. Variance covariance matrices are positive definite. Symmetric positive definite. Okay. Okay, so for any symmetric positive definite matrix sigma, okay, we can find a triangular matrix A so that AA transpose equals sigma. All right, and what we'll do is we'll let A equal, for our triangle, we'll just call it these terms. So we're going to just create a triangular matrix here, and what we want is AA transpose to equal sigma, okay? Which is equal to sigma 1, 1 squared, sigma 1, 2, sigma 1, 2, and sigma 2 squared. Not 1, 1. It's just sigma 1 squared. So that's what we want. Okay, so AA transpose will look like this. So this is A, and A transpose will look like this. And then when you multiply these together, AA transpose, you'll get T11 squared plus 0, okay? And then you come down to, you multiply this by this and this and this, and you'll get T11, T12 plus 0. And here we have T11 and T12, and here I have T22 squared. Okay, and in here I have sigma 1 squared, sigma 1, 2. We'll set this equal. All right, and so now I have 3 equations, 3 effective equations, and 3 unknowns, actually. Well, anyway, there's a bunch of these things, but we can kind of solve these, and we can say, well, okay, T11 will equal sigma 1, right? So we can, we'll just, here, I'll just take the 3 equations that we get, okay? So T11 equals sigma 1 squared, all right? And so this will reduces to T1 is equal to sigma 1, okay? So that's one equation. And then next, I've got T11, T12 is equal to sigma 1, 2, right? And so plugging in the value that I got earlier, I have sigma 1, T12 is equal to sigma 1, 2. And so I get T12 equal to sigma 1, 2 over sigma 1. Okay? And then the last equation, I mean, this one is the exact same thing here. And we'll have T22 squared is equal to sigma 2 squared, okay? And oh, I'm sorry, I messed this up. This is not correct. Nobody caught me. When you do the multiplication, this should be T12 squared plus T22 squared, okay? Okay. All right. And then so now I have sigma 1, 2 over sigma 1 quantity squared plus T22 squared is equal to sigma 2 squared. So you get T22 squared is equal to sigma 2 squared minus sigma 1, 2 over sigma 1 squared. And this reduces to this. Well, not reduces, but this is how we solve it there. Okay, and so with this, and this, we have the terms that we need for our lower triangular matrix A. All right. Okay, so so X is defined as B plus matrix A times Z, and again, Z is Z1 and Z2, where they are drawn from the independent bivariate normal, okay? And then you let B equal the vector mu1, mu2, and then let A equal this matrix. You plug in sigma 1, and now you have sigma 1, 2 over sigma 1, 0, and did I mess something up? Sigma 2 squared minus sigma 1, 2 over sigma 1 squared. Okay. And if you do this, then you will get values generated from the bivariate normal. Okay, let me just kind of do a quick demonstration here in R, and then I think I'm going to do a physical attendance roll call afterwards. We'll just make sure here it says 114 people are here. We'll stick around and see if everyone actually is here. If anybody walks through this doors, I'm gonna like stop them and say like, "Hey," so don't text them to try to run into class right now. Okay, all right. So let me just show you. So we'll have Z1 be our norm. I'm gonna do like 100 Z1, and Z2 will be 100 random values of random normal. So these are independent, drawn from the standard normal. Okay, and then let's say we want mu to be equal to the vector 1, 2. So B will equal 1, 2. And then let's say we want sigma to be, I don't know, 1.7.71, okay? So in that case, we have to do a little bit of math here. T11 will equal 1, and T12 is equal, so according to our notes, it's going to be the covariance 0.7 divided by sigma 1, so that's going to be 0.7, and then T22 is equal to the square root of 1 squared minus this ratio 0.7 squared, okay? So it'll become so T11 is 1, T12 is 0.7. Okay, so if I do this and I let A equal a matrix of T11, T12, T12, I'm sorry, 0, and T22 with n row equals to 2, what I'm hoping, if I did my math correctly, A times transpose A will give me the matrix I want. Okay, so that's what I want, right? So AA transpose gives me the variance covariance matrix that I want. And so we're going to have, so the transformed is going to be we have B is 1, 2. Okay, so I think I have to, I'm going to R bind Z1 and Z2. This will be our Z, and I'm going to, oops, okay. I've got Z, Z1. I think I have to make this a matrix. B is there. I get that, I get that. Okay, and then so X will be defined as B plus A times Z. Non-conformable arrays, of course. Okay, wait, let me just see. What are the dimensions of Z? 2 by 100. Oh, and the dimensions of B is 2 by 1. So I need to extend B. So B, I just need to, because the thing that's going on is Z itself is it's 2 rows, and I have to do like kind of each value. So I just need to extend B. I don't know what's going on there. Okay, I need to extend B by kind of, I don't know, what is it going to be? Matrix of 1 by 100? Matrix of 1s, n row equals 2, n columns equals 100. Will that work? Okay, you know what? We're going to run out of time. I'm sorry. I'm just struggling with I think I can do outer multiplication just by a vector of 100. Okay. All right. Of course, I can't. I'll have to come back to it. I'm sorry. I think I've got to do the attendance thing right now. So, okay, let's. Let me. Okay, I'm going to go ahead and unplug the screen, and then. Oh dear. I hope this doesn't cause my